No. Okay. So we'll start to this session over here. So before I start, I must say that I expect that you guys join in the live session. Uh, the attendance is very less, so please join in the live sessions. Otherwise, it will be difficult in your during your exam per se. Anyhow, so you can go through the recorded lecture video afterward, but it is beneficial for you if you are attending the live session itself. So yeah, keep that in mind. So today, what we will go through in terms of uh, just like just like the earlier weeks, we will have few numericals, few numericals of whatever contents have been covered in your earlier week of this melting efficiency, heat transfer efficiency, those aspects, and at the same time, we will cover a little bit of theory part in terms of different process parameters of welding, which will affect your melting rate, right? The deposition rate, and those aspects, and finally, a little bit of different kinds of welding techniques, particularly gas welding was covered, right? So we will go one by one. So before I start those numericals, let us do some recapitulation of those theoretical aspects, right? So let us start from something called melting rate. Mhm. So what is melting rate, or how we can define a melting rate? So melting rate is basically a resistance setting of the electrode. If you are applying some welding current, which will be supplied through your electrode, and then it will be supplied through your arc, and from arc to workpiece, there will be flow of current, right? Because of flow of electricity. So melting rate is basically results from your electrical resistance setting of your electrode by the welding current, which will affect the uh, which will affect your electrode melting rate. So I can define it by electrical resistance setting, right? So I will define it by electrical resistance setting, and there is some particular empirical formula through which you can define melting rate and estimate what is my melting rate in terms of kg per hour, right? So depending on your polarity, depending on your metal you are using as your electrode, your melting rate can be changed. Now, this empirical formula is defined as AI plus BLI square, right? So A and B are some constant of proportionality. So A is called constant of proportionality for electrical resistance setting, uh, and B is called constant. Sorry, A is called this anode or cathode constant. Pardon. So anode and or cathode constant, that is my A, and B is called this constant of proportionality for electrical resistance setting, right? So this is called constant of. Now researchers have estimated the value of A and B depending on your polarity and uh, different kinds of materials, right? So there is this material polarity combination. So you can use some aluminum, you can use mild steel, and based on those metals, either you can use those electrode positive or electrode negative, right? Straight polarity or reverse polarity, and depending on polarity, they have estimated this value of A and B, and depending on this, here L is my, what is L? L is electrode extension. So L is electrode extension. Now, what is electrode extension? How can you define? How can you define a electrode extension? So every time you, let us say you're doing some arc welding or something, some kind of shielded metal arc welding, right? So you will have some feeding of feeding of your electrode, feeding of your electrode like this, right? And there will be some kind of tube over here and shielding as protection like this, right? So from this end to this end, the extension of the electrode, what is outside of your outlet, outer tube or outlet tube. So this is my outlet tube through which this electrode is passing. Uh, this length is called the extension length. Depending on your length, you can change your resistance also, right? So that is there. Now, how this voltage and current affect my metal transfer, right? So if you are varying your voltage and current, you are changing your metal transfer rate also. So what will be the effect of current and voltage on your metal transfer? So uh, let me draw first. Let's say this is my current and this is my drop per second, right? So let's say the characteristics is something like this. So with increase of current, my uh, rate of deposition is getting increased. Let's say this is one of the voltage. So if I something like this. So basically, if you are increasing your arc current, you are also increasing your drop transfer, right? Because increasing the current, uh, it will increase the it will increase the burn of rate of the electrode. Now, at a constant current, if you are increasing voltage, so if you increases voltage, let's say I'm increasing my voltage. So V2 is greater than V1. Now, at a constant current, my drop transfer rate decreases if voltage increases. So at a constant current, drop transfer rate decreases as V increases, right? And also if your I increases, your drop transfer rate will increase, right? So those are very logical concepts of this effect of your voltage, effect of your current on your metal deposition rate or melting rate, right? Now, of course, there will be having some effect of polarity on your metal transfer also. So these we have talked about a lot on what will be the effect of electronegative uh, polarity, what will be the effect of electrode positive polarity. Now, whenever you are using this electrode as your negative terminal, so let if you are using electrode as your negative terminal, so I'm talking about DCEN. So whenever you are using this electrode negative terminal as happen in gas metal arc welding, so that will result in some kind of spatter formation or unstable arc, right? And the drop size will be big enough, and because of that, you will end up with something called repelled metal transfer. So if we are talking about this repelled metal transfer, anyhow we talked about this in our earlier class also in terms of this repelled metal transfer. It does look something like this. So if this is my electrode, this is my electrode, and this is my R, there will be repelling of the metal transfer, and it will repel away from this center region, right? Yeah. So repelled metal transfer is basically kind of some kind of force that directs the drop away from your weld pool, and then the repel transfer is occurring. So this is transferring from your weld pool and going at the periphery of your arc, right? So this happens when your drop size is very big enough. So my drop size will be big, spatter formation will be there. So those are some common characteristic, or you can say some aspects of this electronegative polarity. So there will be this spatter formation. Those are there. Um, you can come up with some kind of spray transfer where those globule formation will be very fine. So spray transfer may be observed if you are using some argon shielding consumable electrode arc, right? So it appears that argon provides some unique plasma property. So they help to develop this axial spray transfer through the arc. So argon shielding can provide spray metal transfer, right? So this is for electrode negative. Now, what will happen if my electrode is positive? What will happen if my electrode is positive? So that will be the opposite one, right? So it will be just wait. So if I am using DCEP, my arc will be more stable, arc stability will be higher. And I will end up with something called spray metal transfer, right? Where my droplets will be very fine enough. Uh, yeah, so with DCEP, if you're varying the current, with varying current, your drop transfer rate also will be varying, right? So we have talked about this. At low welding current, the size of the droplet, if you are using some, let's say you using some argon shielding gas, right? Uh, they develop they develop a droplet diameter which will be more than a diameter of the electrode. So we talked about this amount of or this droplet dia will be fine after a threshold current is reached, right? So this is my current. So after some threshold current, there will be this change or there will be transition from globular transfer to this spray transfer, right? So at low welding current, there will be this my droplet diameter will be more than this electrode dia. So droplet dia will be more than electrode dia, and I will end up with globular transfer, globular metal transfer, right? And yeah, so with long arc length, if you are using some arc length of larger arc length, the droplets are transferred without any short circuit, right? And at higher current, so at higher current more than what you doing for this globular transfer, the spray transfer appears. So here the tip of the electrode becomes pointed. So there was this change in area of this electrode tip. They becomes pointed, and the drop or transfer at a rate of about some 100 per second, or so the rate will be very high over there when you are using the drop spray transfer, or the very fine droplets will get produced, right? And this current, this is called transition current. So these things we have already talked in our earlier videos, right? So then we have different gas aspects also. So if you are using different shielding gas, it can also affect your metal transfer rate. So we have this helium gas, then active gases are there like carbon dioxide or nitrogen. So we have helium, CO2, nitrogen. So those gases are there. Although helium is an inert gas, they do not produce this axial spray transfer. So with if you are using helium gas, the transfer will be globular in nature, right? Now helium, if you're using helium, they provide, so weld penetration will be higher. So those are few characteristics of those gas aspects. So my weld penetration will be higher over here. Globular transfer will be produced. You can come up with some spray transfer. Spray transfer can be obtained. by mixing argon gas, right? So if you mix argon with helium, you can come up with you can change your deposition rate and size of your droplets. Then if you are using this carbon dioxide or nitrogen, they also do not produce spray transfer. Rather, they will form this spatter when you are doing joining. So if you are using CO2 or nitrogen, so their active gases and spatter formation will be higher over here. So spatter formation will be higher, right? And when you are using electrode as your negative, as I was saying, and at the same time, if you are using carbon dioxide or nitrogen as your gaseous atmosphere, the instability of the arc or the massiveness of your spattering will be very high at that point of time, right? However, you can end up with some kind of spray transfer kind of thing that can be achieved if you paint your surface with some sodium kind of element, and you are using this carbon dioxide shielding, and you are using this negative polarity, at that point of time you can end up with some spray transfer also, right? Now there are some application of these gases as a shielding medium. So mainly carbon dioxide when you should use if you are using mild steel as your object, right? So carbon dioxide can be used to shield arcs in mild steel. Then nitrogen also useful, that can be used mixing with argon to shield aluminum alloys. So you always have some particular application when you should go for these active gases. So I will note it down over here. Shielding of still mixing with argon and shielding of aluminum, right? So those are there. Okay, how about doing some numericals now? So we have talked till now on this metal deposition rate, different aspects of metal deposition rates, effect of this voltage and current on your metal deposition rate, effect of different gas shielding on your metal deposition rate, effect of polarity on your metal deposition rate. Then let us move to this numerical aspect where we will talk about this heat transfer efficiency, melting efficiency, those aspects. So we will try to figure out things in terms of numericals, right? Anyhow, you have gone through those videos. So there we have talked about this heat transfer efficiency, then you have melting efficiency, right? So let us try to figure out uh, what is there in numericals. So in my first numerical, I have talked about this voltage length characteristics and finding out what would be my OCV and SCC. I'm not again uh, explaining in terms of what is open circuit voltage and short circuit current. Anyhow, so it says that my linear voltage arc length characteristic of the welding arc, that is given as with some linear relationship. So that is given as E is equal to 20 plus 2L, right? Now I have told that during welding the measured arc current is 500 ampere corresponding to an arc length of 5 mm. So let's say L1 is equal to 5 mm and corresponding I1 is 500 amp, and the measured arc current is 460 amp corresponding to an arc length of 7 mm. So L2 is 7 mm, I2 is 460 amp, right? Then I say that if the welding machine follows a linear power source characteristic. So if my welding machine is following a linear power source characteristic, so V and I is following a linear power source characteristic. So it will follow a relationship of V by OCV plus I by SCC equal to 1, because this follows a linear relationship, right? Those we have already described. Now we have two equations. We can find out two equations. So let's say this is V. This is the voltage. So my V1 is equal to how much? 30 volt at L equal to 5 mm. V2 will be how much? 34 volt, right? At 7 mm, right? So we have two equations. We have two unknowns, right? So V1 by OCV plus I1 by SCC equal to 1. That is my equation 1. And V2 by OCV plus I2 by SCC equal to 1. That is my second equation. Can you guys solve those two equations and give me some value of OCV and SCC? I'm not done this. Why don't you go for it? So you have those V1 value, you have that I1 value, V2 is also known, I2 is also known. You have two equations. We need to find out OCV and SCC. It's simple linear relationship. So yeah, straightforward. You can ask me if there is any confusion. Please solve this. T by OCV, so 500 by SCC, 1, and 34 by OCV, 460 by SCC, equal to 1. So from here I can get that OCV by 30 equal to 1 minus 500, sorry, it will be 1 minus 500 by SCC. So SCC will come up Are you agreed till this? Can you guys please respond so that I can understand, you can hear me or okay. So I will end up with some equation like this where OCV will be OCV will be 30 SCC by SCC minus 500. So whoever will be watching this video later also, please, I suggest that do the maths from your own. Otherwise, it will be very difficult to get it done. So if my OCV is coming as 30 SCC by SCC minus 500, you get the OCV. It simply then put the OCV in your equation 2. So I will come up with some 34 into SCC minus 500 by 30 SCC plus 460 by SCC. That will be equal to 1. From here, I can simply find out my short circuit current, right? So, okay, let me solve this. So, 34 SCC minus this. So, 34 SCC. 17,000. That is into 30 SCC. Yeah. So, my I'll end up with some equation, right? Yes. So, my short circuit current is coming as 800 amp. So if you are getting your short circuit current, you can simply put the value of short circuit current in either of your equation and get the value of OCB, right? I hope this should be clear. So we'll move to the next part. So what is mentioned over here? We have said that in case of arc welding of steel, uh, the potential is provided as 20 volt, current is provided at as 200 amp, and I say that the travel speed is of 5 mm per second, right? And I have also provided the cross-sectional area of the joint. It says that heat required for melting steel may be taken as 10 joule per mm cube. So I have provided this the heat required to melt the material, right? So from there I can simply find out what will be the total heat required to melt the material. If something is given in terms of unit volume and you get the total volume of the or the melt volume as such, so you can get the total heat to melt the material. No. So my sorry, my voltage is 20 volt. My current is 200 amp. So what will be the total heat supply to the workpiece? If you know your voltage and current, we can simply find out what is my power which is going or the heat supply which is going into my workpiece, right? And you need to supply it by something called heat transfer efficiency. So my total heat supplied to workpiece will be heat transfer efficiency into voltage into current, right? This is my power and I will multiply with my heat transfer efficiency. Is there any confusion? On getting response. Okay. So so my total heat supply to the workpiece will be the heat transfer efficiency into voltage into current. So I must say from the next week onwards, please do attend the classes. And if you guys don't respond, it will be very troubling for me to give some lecture, right? So please do attend. Anyhow, the videos are getting recorded and you're getting it in YouTube terms, but this is really pathetic. Uh, so my total heat supply to the workpiece will be this heat transfer efficiency into voltage into current. So this is my power supplied, right? So this is my power supplied. Now I say that heat required to melt the material, sorry, that is given as 10 joule per mm cube. I have provided the cross-sectional area as 20 mm square and also I have provided the travel speed. So velocity is 5 mm per second, right? So if melting efficiency is nearly 30%, what will be the heat transfer efficiency? So my melting efficiency will be heat required to melt the material and total heat supplied to workpiece. So This will give me 10 joule per mm³ into 20 mm square into 5, right? This gave me the total heat which will be required to melt the material. I can get the volume, and then that is multiplied with the heat required per unit volume, and that divided by heat transfer rate into 20 into 200, right? So how much is this coming? So I have told that melting efficiency is 0.3. So my melting efficiency is 0.3, and this will be coming as 200 into 5, that divided by heat transfer efficiency into 20 into 200. So this will be coming as 0.3 into heat transfer efficiency is equal to 0.25. So my heat transfer efficiency will be coming as 0.3. That is coming something around 0.83. So 83% will be my heat transfer efficiency, right? So what is melting efficiency as actually? So that is the ability of my heat source to melt the base metal. If you are using some filler metal, uh, you need to melt base metal along with your filler metal, right? So my melting efficiency will be the heat required to melt the filler, that addition to heat required to melt the base metal, and that divided by the total heat supplied, right? So if you are using some filler material, so let us go to this next part of this numerical. Let me first drop this out. So if we have a filler metal as well as a base metal, let's say this is my filler and this is my base, right? So what will be my melting efficiency? My melting efficiency will be heat required to melt the base metal per unit volume into volume of the base, that plus heat required to melt the filler per unit volume, that into volume of the filler, whole divided by eta heat transfer into V into that is my voltage actually. So let me voltage into current, right? That will be my melting efficiency. Now in this question I asked that in a submerged welding operation, I have provided the electrode dies of 8 mm feed rate, so electrode feeding rate. So you know that in automatic welding you can there must have some feeding rate of your electrode, right? So I have provided that electrode feed rate as 10 mm per second. Welding speed is provided as 20 mm per second, and total weld cross sectional area. So A filler plus A base. So A total with A filler plus A base, right? So total weld cross sectional area is provided as 30 mm per 30 mm square. So I have asked what will be the base metal cross sectional area. So if we have somehow find out this filler metal area, I can get the value of base metal area which will be melted, right? So how can you get the value of filler metal area? So we can find out this filler metal area. So if we have this cross sectional area of this filler, let's say A filler, right? That into welding speed, that into time, the same thing will be equal to, if you know your electrode dia, that is going to be fed in your workpiece. So let's say R is my electrode dia. So R electrode. So pi r square will be my cross sectional area of filler. That into V filler, which is the feed rate, right? And that into T. Those are basically welding time. So you can neglect those weld times in this equation. And finally, we end up with some equation of my filler metal area will be pi r square into filler, that is my feed rate, that is my feed rate, and this is my welding speed, right? So then how can you get this value of A filler? So my A filler will be equal to what? Pi into r square into how much is the feed rate? This is 10 mm per second and simply 20 mm per second. So I'm getting it as 2, 8. So 8 pi mm square is my filler area. And then this is something around how much? 3.14. So it's something around 25 mm square. Let's say this is something around 25 mm square. I'm not going to the exact value. Uh, Anyhow, so if your now total weld cross-sectional area is 30 mm square, you get the value of filler area. So from there we can simply find out that the base cross-sectional area will be A total minus A filler. Right now. So that's how we can come up with this finding the value of base metal area. Okay. So next we will next we will talk about this different kinds of welding parameters and their effects on your weld quality and weld deposition rate, right? So both are influenced by those welding parameters like current, voltage, speed, feed rate, extension, electrode dia. So all those stuffs, right? We have another numerical. So let us finish the numerical first. The concept is similar. I have asked the heat transfer efficiency in arc welding of a plate. I have provided the current, I have provided the voltage, and heat transfer efficiency is also provided. So you can find out the total heat input, right? So total heat input will be heat transfer into V into I. That will be 0.9 into 20 into 250, right? Now, I have provided the melting efficiency as such, and I need to determine the heat required per unit volume to melt the material. So if I know the melting efficiency, so this will be heat input per volume, which need to be calculated, that into total volume of the material which will be melted, right? And that divided by 0.9 into 20 into 250. And then I have provided this cross-sectional area of the weld joint, weld travel speed as 5 mm per second. So I can find out the uh, volume of the melted material, right? So if my melting efficiency is 0.5, let's say this is, let's take it as x into 30 into 5, that divided by 0.9, 20 into 250, right? How much is this coming? So it's something like I am preparing the question, I am only answering. So how much is this coming? So 30x is coming as 0.5 into 0.9 into 20 into 50, 0.45 into 1000. That is 450. So x is equal to 150. So my heat required per unit volume will be, this is huge actually. So anyhow, uh, ignore the practical values and just get the concept of this numerical. So I'm getting my heat required per unit volume as 150 joule per mm cube, right? Now, now we have talked about this. Current is directly proportional to this melting rate, right? So if you are increasing your current, your melting rate uh, that is directly proportional to your energy actually. So part of this energy is used to melt the base metal. Some part gets lost in terms of convection and radiation, and some part goes to melt your electrode and flux and those stuffs, right? And this convection, conduction, radiation, those parts are dissipated, right? So your total, always you do some calculation of what will be my uh, total heat energy. So that will be always equal to your, so my Q total will always equal to the heat input to melt the base metal if you have some flux or some electrode which is getting melted, that heat, then you can have this convection, radiation, and what else? The conduction part, Q conduction, right? And that is equal to my into, you can think it of in terms of I square R also. So R is my arc resistance, right? So we talk about VI. The same thing is if you are uh, equating this as IR, so my total heat loss will become as I square R, where R is my arc resistance, electric arc resistance, right? So my current will be the most affecting variable, which will affect my melt rate, which will affect my deposition rate, which will affect my uh, weld bit width, which will affect my depth of penetration. So everything is connected to this welding current, right? So if your current is too high, there will be excessive penetration, right? So that should not happen if you're join some thin plate, so it will get melt through, right? If you're supplying lot of current, there will be excessive penetration of your weld, and basically the complete plate will get damaged if it is thin in nature, right? Now there will be excessive melting of your electrode, and more heat input to plates being joined, that increases distortions also. So there are some different aspects of this residual stress and distortion, those aspects. But yes, so if you're increasing welding current, there will be much more weld penetration, much more melting, and weld distortions will be very high. At the same time, if your welding current is too low, what will happen? The penetration will be inadequate, right? The melting will be inadequate. There will be some defect which is due to lack of fusion, right? The melting will not be adequate enough to join the material, right? So those parts are there. So you have to optimize your welding current in a way that it will provide uh, all those outputs in a very optimal condition. So my weld penetration should be within some range. My weld distortion should be in some range, uh, so that it doesn't hamper your workpiece, right? So yeah. Now, now what will happen in terms of arc voltage? What will happen in terms of arc voltage? So what does voltage depend on? Voltage depend on the length. So it depends on this electrode extension or the arc length, right? If my length increases, arc resistance will get increased. That results in a higher voltage drop, right? So arc voltage increases at that point of time. So proper arc length. So obtaining some proper arc length is very important to get some sound joint, right? If your arc is short in nature, what will happen? There can be some short circuiting during the metal transfer. If your arc is large or long enough, what that will do? It lacks direction, it lacks intensity. So there will be scattering of your during your weld formation, right? There will be formation of undercuts. So it will form some undercuts like this. So these are called undercut. And this happens if your arc length is very large, and the bead appearance is highly dependent on this arc voltage, right? So if you're increasing arc voltage, they tend to cause some porosity, scattering is there. So there will be bit increase in your bead width. So if we try to figure out if you try to figure out how the weld bead shape will change, how the weld bead shape will change. So let's say this is one of your weld bead. This is another weld bead. This is much wider. The depth also is there. So if this is done at V1, this is done at V2, this is done at V3. V3 is the highest one. Enough. So increase in arc voltage will cause this porosity scattering. And at the same time, if your arc voltage is getting reduced, that leads to this very narrow weld formation. The crown will be higher, right? So those aspects are there. So if your voltage is increasing, it forms porosity, it forms spatter, and if my voltage is getting reduced, weld weight will be narrow. So those are some simple, straightforward aspects of effect of voltage and current uh, on your bit width, deposition rate, and penetration depth, scattering, and those aspects. You know. So yeah. Now what will happen in terms of welding speed? So welding speed generally conforms to given combination of welding current and arc voltage. If you are doing your welding with some specific combination of current and voltage, uh, how welding speed will affect your bid appearance, right? So if welding speed is more than what is required, uh, your heat input to the joint will decrease, right? So your metal will get less amount of time where it will be there at a fixed temperature. So let's say this is my top view and the contour is something like this. So we call it temperature contour, right? So if you are moving at a very slow speed, if you are moving at a very slow speed, what will happen? My heat input per unit length will increase if V is less, right? So your weld width will increase, uh, the reinforcement height also will increase, but at the same point of time, penetration decreases, right? So penetration decreases beyond a certain decrease in speed. So this will give you some large weld pool and a rough bead appearance. At the same point of time, if your welding speed is very high, your heat input per unit length will get reduced, right? So heat input per unit length will be reducing, right? So there will be uneven bead shape and arc blow can be there, undercut can be there. So those defects can form if your welding speed is very high. So each and every time you need to optimize your process parameters to get some uh, good bit appearance, right? So yeah. Now, one more thing I want to mention over here. Let's say you are keeping all the variables at constant, right? So and you are changing your welding speed. So with all variables held at constant, your weld penetration depth that will attain some maximum at a intermediate speed. And if your welding speed is excessively low, the arc strikes a large molten pool, and your penetrating force that get cushioned by your molten pool. So if your welding speed is very low, let's say my welding speed is very low, very low. So molten pool will be very high, and the penetrating force get cushioned by that pool, by the molten pool. है ना? Now, if your welding speed is excessively high, there will be a drop in your thermal energy per unit length, as I was saying, and that will result in the undercut. So that is there. Now, your electrode extension and electrode feed rate, those also will affect your bed appearance, right? In most welding machines, the welding current adjusts itself with electrode feed speed to maintain that arc length in automatic or semi-automatic welding machine, right? Now, in terms of electrode extension, uh, I mentioned that that is the distance between the end of the contact tube and the end of the electrode, right? So if there is an increase in your electrode extension, that will result in your increase in your electrical resistance, right? If my length is getting increased, my resistance will also get increased. And this causes resistance heating of the electrode extending length, results in a additional heat generation. So my electrode melting rate at that point of time will be increased due to this additional heat generation if I am increasing my electrode extension, right? But uh, at the same point of time, the energy consumed by the electrode, it will reduce the power delivered to the arc, and which is getting transferred to the workpiece, right? So because my electrode is getting melted and it consuming energy which should get transferred to the workpiece, my workpiece will get heat less enough, and because of that it will decrease the weld bit width, it will decrease the penetration depth and those aspects, right? So if you are increasing your electrode extension, I will end up with a decrease in weld bit width, weld penetration depth will also decrease, right? So yes, and yeah, those are there. So I will come to the gas welding part later. So let us skip question 4 as of now. Question 5 we have solved. Yeah. Which of the followings are true? With decrease of electrode extension, which of the followings are true? With decrease of electrode extension, electrical resistance decreases. Yes, this is true. With decrease of electrode extension, that results in additional heat generation. No, my additional heat will be generated if my resistance is getting increased. So for that, you have to increase the electrode extension, right? So this is a false statement. And with decrease of electrode extension, it decreases the bit width. This is also a false statement. Sorry, this is a true statement. So because no, sorry, with decrease of electrode extension, no. So with decrease of electrode extension, my penetration uh, depth will be higher. That is a true statement. So this is false. So basically, those are vice versa uh, in mechanism, right? So if my electrode extension is higher, it will give me higher resistance. Uh, because of higher resistance, it will generate more heat. Because it is consuming more heat, less heat will get transferred to the workpiece. Because less heat is getting transferred to the workpiece, the bead appearance will be lower, right? Bead width will be less, penetration depth will be less, those things. So question 6 is fine. Then I say in question 7, which of the following are true? High amount of current is beneficial for thin sheet joining? No, this is false statement. Reduction in arc voltage leads to narrow weld bit? Yes, this is a true statement. I have talked about this. Reduction in arc voltage will lead to narrow weld bit, and slow welding speed results in increase in heat input per unit length. This is also a true statement, right? I will come to this question 8 later because this is part of gas welding. There is another numerical that is also some straightforward equation solving, right? So here I have asked to find out this electrode extension if the melting rate is 2 kg per hour while the current is 200 amp. I provided those constant of proportionality, right? So at the very initial phase of this lecture, we discussed about this melting rate. What is my melting rate? My melting rate is equal to AI plus BLI square. Where L is my electrode extension, I is my current, and A and B are the constant of proportionality, right? So these we have already talked about. Now I have provided this metal as aluminium, and I am using electrode positive polarity, where for those this for this empirical formula, A and B values are provided for this metal and polarity combination, right? So if my melting rate is provided as 2 kg per hour, and this is given as 5.4 E minus 3, that into 200, that will be kg per hour plus 4.4 E minus 6, that into, I need to find out the electrode extension, that into 200 square, right? So how much will be this? I do not have calculator over here, but yes. So 5.4 into 200, 24825. 10. This is coming as 1.08 plus 4.4 into 2 4e4, right? So 4.4 into 4, which is coming as 0.176 into L, right? So 0.176 L will be 2 minus 1.08 and get the value of electrode extension. From here, I can get my electrode extension. As simple as that, right? And then over here, I asked that which of the following are true? If our current increases, drop transfer rate increases. This is true. This is true. DCN makes the Earth's battery and results in repel metal transfer. This is also true. I have talked about this. Active gases do not produce ray transfer. This is also true. So all of these statements are true, right? Now let us move to this. So in the earlier week, professor has covered this gas welding or oxyacetylene gas welding aspect. So we will discuss a little bit on this gas welding, different kinds of flames, different components of gas welding in terms of what are the different gases, what you need to provide in terms of pressure regulator, gas hoses, um, those aspects, and how your flame will look like depending on your ratio of your mixture of those two gases, right? So those things we will cover in very brief. So what is gas welding? That is a welding process that will uh, melt and join your metals by heating them with a flame, right? So this is a flame heating process which will be caused by this reaction between this fuel gas and oxygen, right? So oxyacetylene welding, here you are using acetylene as your flame material, right? So you can use other gases also, but yeah, this oxyacetylene flame is mostly used in industries and most commonly used to gas welding process because of its high flame temperature, right? So you can use some kind of flux that may be used to deoxidize or clean the weld metal. So basically, if you're using flux, your flux also will get melt and solidified, and it forms some kind of slag skin on the resultant weld metal. So there will be this slag formation, right, which will protect your weld pool. So you know those concepts. Now, what is there in gas welding? What is there in gas welding? So uh, let me draw. So you'll have a cylinder. I'm having a cylinder of acetylene. I'm having a cylinder of oxygen. Then I will have some pressure regulator over here. So I'll have some pressure regulator like this, and I have some pressure regulator like this. Then from here there will be flow of oxygen gas. From here there will be flow of acetylene gas, right? Then I have some valves over here. Then I will have those. So this is basically my mixing chamber where I will mix those two gases and create uh, those chemical flame by this reaction of those two gases, right? And then I am having some torch. I'm not going into detail of different kinds of torch as such, but yeah, you can come up with different kinds of torch, and they have their particular application on welding. Uh, if you are applying more amount of oxygen for that, you will end up with some different torch, right? So there will be some additional folds provided. holes provided to provide this oxygen, excess amount of oxygen, which will help you in cutting operation. So that is something called oxygen cutting. So those things are there. And then you have this workpiece, work material over here. You can fill a rod. So this is a typical oxyacetylene gas welding setup, right? Now you must have kept this acetylene in a confined space. So acetylene can be decomposed in carbon and hydrogen, uh, right? So this decomposition, if it is getting decomposed into carbon and hydrogen, that results in high pressure. So when your pressure reaches a certain value around some uh, zero point 0.2 megapascal, so this mixture of carbon and hydrogen becomes uh, violently explosive, right? Even at the absence of oxygen, right? So this happens when this mixture is subjected to a spark or shock, those kind of stuffs. And to avoid this problem, always acetylene is dissolved in acetone. So this you should keep it in mind. Acetylene is always dissolved in acetone, right? So yeah, that is there. Um, so an excess of oxygen or acetylene can be used depending on whether you want to generate some decarburizing flame or a carburizing flame, right? So there are three different kinds of flames. So if I talk about flames or generation of flames in gas welding, there are three different kinds of flames. What are those? They are neutral flame. What else? We have reducing flame. We have oxidizing flame, right? So in neutral flame, the oxygen and acetylene are mixed in equal amount. This is very well known, and they're mixed in equal amounts, and they're burned at the tip of the welding torch, right? So how you can characterize a neutral flame? So your inner core will be short, means the length will be inner core will be very short, and a longer outer envelope will characterize a neutral flame. So how will it look like is something like this. So I am having inner core, short inner core, and longer outer envelope, right? So that's how I can characterize a neutral flame. Now, the inner core is the area where the primary combustion takes place, right? Through this chemical reaction between oxygen and acetylene, right? So the heat of this reaction accounts for about two-thirds of the total heat generated, and you know that the products of this primary combustion are carbon monoxide and hydrogen, and those react with your oxygen from the surrounding air to form this carbon dioxide and this H2, right? So that is my secondary combustion. The primary combustion takes place at this inner core by forming this carbon monoxide and hydrogen, right? So uh, the area where this secondary combustion takes place, that is called my outer envelope. So over here, my primary combustion takes place. Over here, my secondary combustion takes place, right? So yeah. So this outer envelope is also called protection envelope. We call it protection envelope also, since carbon monoxide and hydrogen here uh, consume this oxygen entering from the surrounding air and hereby protecting your weld metal from oxidation, right? So that is there. Now, what is there in reducing flame? In reducing flame, you have excess amount of acetylene, right? So the resulting flame is called reducing flame. So the combustion of acetylene is incomplete over here. So in your reducing flame, combustion of acetylene is incomplete, right? So as a result, there will be different color of this flame. It comes up with this greenish kind of uh, greenish color of this acetylene feeder, which will form between your inner core and outer envelope, right? So if you somehow, I don't know you have seen or not, so there will be some, so I will be having this inner core, I will be having this outer envelope, and there will be some uh, green feeder, greenish kind of acetylene feeder. We call it acetylene feeder. So this is my reducing film, right? I will not take much time. So when you should use this reducing flame? So this flame is desirable for welding some aluminium alloys, right? Because aluminium can oxidize very easily. It is also good for welding of some high carbon steel, right? Because excess oxygen can oxidize carbon and form carbon monoxide CO gas, and it forms porosity in your weld metal. So those aspects are there when you should go for this reducing flame, right? And then you have this oxidizing flame. Oxidizing flame is used when you have this excess amount of oxygen, right? So the flame becomes oxidizing because of the presence of this unconsumed oxygen. So how you can characterize this oxidizing flame? You'll have a short white inner core. So my inner cone will be very short in nature. This will be very bright and luminous. This inner core will be very bright and luminous when you are generating this oxidizing flame. So it will be bright, white, luminous, right? So yeah, okay. So I will make it very brief. So let us finish it over here. Uh, we had some questions on we have some questions on gas welding. So we have to identify the correct and incorrect statements with respect to oxyacetylene gas welding. It says the temperature of a carburizing flame in oxyacetylene gas welding is higher than that of a neutral flame. Is this correct? This is not correct, right? Reducing flame will give me lower temperature than the neutral flame. Oxidizing flame will give me the highest temperature, right? Then I say that welding of iron and steel using carburizing flame in oxidation produces very hard and brittle iron carbide. This is true. In the case of neutral flame, 1:1, this is true. And oxidizing flame contains less oxygen than that required for them. This is false. Because I tell that less oxygen is required, which is not the case, right? So it is there. What else? Which of the following apparatus is used for oxyacetylene welding? We use two pressure regulators, two flexible hoses, and one torch. That's it, really. So, A station. Okay, so we'll finish it up over here. So, I suggest please try to attend the live sessions. Uh, I'll be very happy. I'll be very happy if I able to make you understand those concepts. But yeah, try to try to attend those course, those live sessions, so that it will be beneficial for you only. And go through the recorded lectures. If you have any problem, you can get to me. Yeah. So okay. Bye bye.